Okay. So you see, when we are using all these electronic devices or these chips are no longer manufactured and packaged in the same location. Okay. For example, you see the design of the chips primarily happens in the US. This is what Intel will primarily do, and then the equipments which are used to make these chips are actually manufactured mostly in Europe. Places like Netherlands, Germany, they will actually manufacture these lithography tools to make these chips, right? These are the UV lithography tools. So, and then you have basic materials which is literally coming from different parts of the world. I mean, even not only US but also maybe China has a lot of these raw materials which are required for semiconductor manufacturing. And then you go to the fabrication which happens in mostly nowadays in Taiwan, in Korea, which is Samsung, and in the US, which is Intel, right? So we have literally the three places on this planet where chips are actually the front end fabrication happens, and then they are assembled for testing. So testing and packaging could also happen in places like Malaysia, in Vietnam, these places. And then of course after that it is packaged, it can be sold to anybody, right? The rest of the world. So the chip manufacturing process is very globally distributed. So there's a lot of geopolitics associated with the manufacturing, packaging, and assembling and distribution of the chips. So, and each process is vulnerable because not all countries are going to be equally honest in terms of how are they dealing with this fabrication process, because everything has this intellectual merit. Let's say for example you design a very high-end chip, right? That's your intellectual property, right? You don't want anyone else to claim that that is their intellectual property, right? Because then you will not be earning any money when this chip or your design is kind of commercialized, right? But then in some place where it is going for packaging, somebody could simply open it up and find out what is going on inside the chip, and then they can claim that, oh, I have, and they can design it and then can claim that is my intellectual property, right? So it's a big problem in the chip manufacturing industry. How do you ensure the security of these different chips? And there are different levels of security problem. For example, here you see this is what we call counterfeit ICs. Counterfeit ICs are something which looks exactly the similar. Okay, you see the two ICs are exactly looking very similar, when one of them is actually authentic and the other one is not. Because if you open it up, you will find that the connections are very different. Because what do? You kind of just use these chips and then throw it as an electronic waste. Someone can go and collect it from the garbage and just take the packaging and put their own chip and again repackage it and claim that, oh, this is an Intel chip that I'm selling, right? So they could be inauthentic, they could be recycled, they could be remarked. In fact, you will be amazed to know that the 60% of the chip that the US defense uses, like the Army, Navy, are counterfeit. Okay, so it's very difficult to prevent this thing. So the question is that can we use new design or new materials to solve this kind of problem, right? So that is one problem. The other problem is, you see, this is what we call reverse engineering. This is a term you may have actually heard, right? I mean, and one of the countries, our neighbor countries, are actually expert in doing reverse engineering, right? They literally, kind of take cross-sectional TEM or SEM images of the chip, and then they redesign it, right? And now you don't need to buy it from the US anymore, because now you have your own chip, right? So this is what is called reverse engineering. You just look at the design and then reverse engineering, right? This is again a big problem, because then you lose your competitive advantage. Makes sense, right? This is reverse engineering. So therefore, if you look into the hardware security domain, there are different types of problem. One is the authentication, whether the chip is authentic or not. The second is whether it is recycled or remarked, right? Then it may not be non-authentic, but then it is just that you are reusing it for the more number of times than it can be actually used for, right? So you kind of compromise on the performance of the chip. Reverse engineering, and then as I told you, the intellectual property. These are the things that we wanted to see whether we can kind of tackle these problems using 2D material. And I have written down the solutions, and I'm going to talk about that, this 2D physically unclonable function, anti-counterfeit solution, camouflaging, and the watermark, all using 2D material. So this is a very different area, okay? I mean, this would probably require one full course to cover all these materials, but I will try to give you some glimpses of what has been happening. So we'll start with, physically unclonable function. or the authentication. This is nothing but a password, but this is a hardware password. So generally, whenever you log in, you generally type a password in your account. So if we could create something where you can have a password for every chip, then nobody can actually claim that it is there, right? Because every chip will be associated with a unique password. Makes sense, right? Because like your every Google account, all of you have a Google account, right? Your every account is associated with your username and your password, right? Password is your protection because username anybody could know, right? So the same thing we also have to do for the chips. Make sense? So if, in order to enter that chip or make this chip operating, you have to first put the password. Okay. So this is what is called the physically unclonable function. I will explain what does physically unclonable function mean, but this is a hardware version of password. Okay. So what is a physically unclonable function? It means from the name only you can see unclonable means you cannot clone it, right? Like your password, you cannot mimic it because it's in your mind, right? Unless we mimic your mind, you will not be able to know what password you have used, right? So that is why it is called unclonable. Then we call it physical because it is actually something in the hardware, right? That's why it is physical. It is not a software one. And then it's a function because it is based on some math, but you see we call it a challenge response pair. So the puff is a physical medium. Okay, it could be anything, and I will give you some examples of that. It's a physical medium to which you put a challenge, and it gives you a response. So there is an input and there is an output. Okay, so the input is your challenge. You're challenging that physical media, and it is giving a response. And this challenge response pair constructs this physically unclonable function. Okay, there are two criteria that this physically unclonable function has to satisfy. That for same challenge, if you give the same challenge to different puffs, okay, the response should be different. Okay, and the other one is that if you give different challenges to the same puff, the response should also be different. Okay, these are the two criteria. Now I'm going to show you an example. How can we do that? Okay, the first puff that was discovered, but only 15 to 20 years back. Okay, this paper came out in Science. So here you have a liquid containing a lot of nanoparticles. That is your physical medium or this puff. Okay, what is this puff? It's just a suspension of nanoparticles in a solution. We can all make it, right? Now, this I can use as a physically unclonable function because we do not know, how the nanoparticles are going to be dispersed in this solution. It's like a very chaotic or a random medium. So now if I shine light on this nanoparticles and place a screen in the back, what will it create? It will create an image which we call a speckle pattern, because the light will diffract based on the position of the nanoparticles, right? The light will diffract and I will get an image in the backward, right? So therefore, what is my challenge? My challenge is the light intensity or the light that I am putting in, and the response is the image that gets created. So now I have created a physically unclonable function using a suspended nanoparticle. Make sense? Now let's see whether it's a puff or not, because it has to satisfy these two criteria. Then only I can call it a puff. Just having a medium and having a challenge and response is not good enough. It has to satisfy these two criteria. So let's see the first criteria. The first criteria, what I am saying is the challenge is the same. That means I will keep the light source the same and change the medium, which is this solution with different amounts of different nanoparticles. Will the response change at the background? It will. So it's impossible to know what is the exact position of the nanoparticle even if you make it every time. Correct? So therefore, it satisfies the first criteria, which is your challenge can be the same, but if you change the physical medium, your response in the background is going to change. Is this part clear? Right? Now the second one. Second one is if you use different challenge. What is different challenge? If you just rotate the angle from which the light is coming, then will the response change? It will, because the diffraction pattern will change, because the light will diffract differently. Right? So if you keep the medium the same and simply rotate the angle from which the light is coming, or if you change the color of the light, then the pattern may also change. Right? So therefore, if you apply different challenges to the same puff, the response is different. Make sense? So therefore, we can then use this as a physically unclonable function. But the problem is this is something I cannot use for a chip, right? I mean, where will I get suspended nanoparticles within a chip, right? So what is the solution? The solution therefore is you use silicon devices. This is called optical form, right? Because it's an optical challenge response pair. You can create similar things using silicon actually. What you do is you create these different ring oscillators. These are different clocks that are available within the chip, and each silicon device, right, I mean, might be slightly different. Although they are exactly the same, that's what the manufacturing process has ensured, but there could be some device to device variation. And that may lead to little bit change in the clock frequency. Okay? And then if you create a structure like this, okay, then you can harness that. I'm not going to go into the detail of this because I'm going to give you a much simpler example using 2D material. Okay? So I'm going to go directly to that, where I'm going to use graphene. So we have heard about graphene in this lecture quite a bit. We know this is how the IV characteristics of graphene look like. And then as I told you, if you make graphene, and if it's like a CVD grown graphene, there could be a lot of grain boundaries in graphene, right? Because it's not a perfect single crystal material. Okay? And when you have a lot of grain boundaries, you cannot predict where the grain boundaries are going to be, right? So any material you make, right, it is very difficult. And then if you put two metal contacts and measure the current, not every device is going to give you the same response. And if you measure a lot of devices, look at the device to device variation, right? And generally you will discard this material, saying that, okay, this is useless because I cannot reproduce, right, every time the same IV characteristics, right? And this is useless for anything that I want to make a logic circuit or any form of neuromorphic computing or sensing, right? But this forms the background of physically unclonable function because you are looking for variation. Right? Without having different device to device variation, like different password, password has to be really diverse and variable, right? This can then be used to construct physically unclonable function. Now the question is how? So we see that lot of these parameters, this Dirac point, this different current, they all follow a Gaussian distribution. So that means that they are really random in nature, right? Because whenever they follow a Gaussian distribution or a uniform distribution, we say that they follow some probabilistic law, right? So this can then be used for the these are identical devices. Identical devices where characteristics is different because of the fact that you have grain boundaries, right? You have mobility being different, right? Same condition, same lab. In fact, if you do it again, it will be also different. And this is what you want. For each chip should have a unique signature, right? Which nobody else can reproduce. So even if you give you full recipe of how to make a material, if you go and make it, it will not be exactly identical. This should not change with time. Okay, I will come to that because if your password changes with time without you knowing, so it should not. That is actually the case. Once you make the device and measure it, it remains stable. But it is just that from device to device, there is a lot of variation. That you have to ensure, right? Over the time, you don't have a lot of drift. So now what you can do is you can take an array of these devices, right? And let's say there are 8 devices. So 8 devices will give you 8 unique response, right? Because the device, and here you are intentionally making sure that there is a lot of device to device variation. Right? One approach is to make sure that your devices are all exactly the same, right? That's what we generally work, when we are working with material synthesis or device fabrication. Here the philosophy is exactly the other way around. You want to introduce variation, right? Once you have this variation, then you can literally go. So your challenge now becomes your voltage, and your response now becomes current. Okay, that makes it more possible for me to integrate it with silicon chips because current voltage should be the input and output, not light, right? So now if you challenge it with the voltage, you will get a response which is current, and for any given voltage, you will get a different current, and that you can pass through an analog to digital converter like we kind of did last time, and you can get a unique code, right? So now you have for each array maybe a 64-bit key like the password, right? So now we have generated a physical password. Got it? Now if I go to another array, you see this key is different because the devices over there are going to be also different, correct? So the key is different, and I can keep doing that. So I kind of keep creating new passwords using just these arrays of devices. So now I have created this physically unclonable function, but now I have to test a few things, right? So, and I'm going to go through that, but is this part clear, that how did we use the device to device variation, which is otherwise very bad, for a useful application which is really very needed to ensure the integrity of the semiconductor manufacturing process. Correct. Yeah. Yes. You should have larger matrix. Exactly. So because of the fact that if you have a 2-bit number, then it is 0 or 1. So anybody can predict what is your password has to be between 0 and 1. So therefore the length of the password should be large, right? Because if it is a 4-bit password, only 2 to the power 4 combination. That's why we have made it a 64-bit password. What is 2 to the power 64? That's a huge number, right? So today, you see, are you aware of this RSA encryption? Whenever you send an information through internet, it is encrypted, and it is encrypted into at the beginning and front they put some of these numbers actually, okay, and these are 128-bit long, okay. The problem today is with the quantum computing, because these passwords are software generated using algorithms, there are quantum algorithms which can break into these things very easily, okay, because these are generated classically. Okay, so the thing is that if you have 2 to the power 64, 2 to the power 20, 128, it's such a huge number. Even if you give you a supercomputer, it will take probably 10 years to break or find that password. You see, because it has to really kind of do trial and error a lot of times. But quantum computers are so powerful, they can break it in 2 minutes, right? So hardware security is becoming even more important, maybe 10 years, 20 years down the line when quantum comes into the picture, and quantum cryptography is actually a much bigger interesting area than even quantum computing, okay? Because quantum computers can, so anybody gets a quantum computer, they can break into any of your bank accounts, any of your health information or anything, any personal information can be hacked very easily with quantum computers, okay? Okay, so now the thing is that, okay, this is fine. So we have generated the keys. Now they have to satisfy certain criteria, okay? And you see the number of total challenge response pairs that we can generate, is 2 to the power 64, which is 1.8 times 10 to the power 19. That's a huge number, okay? And you can see that if it just simply increases by the number of bits, it's just going to correct. So 128 will be 10 to the power 38, right? It will be the square of that. Okay, so now the next thing is, okay, we generate these keys using more complex circuits. This is also not always needed. If some of your interest is more, so first thing you can do with any material that you are synthesizing is probably making a puff. Okay, you can get a very good paper in SCS Nano or Nano later, okay, by making a puff. Okay, and it's most likely going to come to me for review as well, because we have done a lot of puffs. Okay, we have done electronic puff, spintronic puff, optical puff, even biological puff. If you're working with bacteria and stuff, we even have a paper where we use the population of bacteria to generate this physically unclonable function. Okay, this is actually a much easier goal to achieve. Now one thing, so we have to test for a few things, right? This has to be really random. Okay, if these passwords are not random, then you can predict it, right? Let's say if the password is 10 ones and then 10 zeros and then 10 ones and 10 zeros, anybody can get to that very easily, right? So it has to be random, and the way to test randomness of a system is called the entropy. Okay, and there's a formula for the entropy, which is this P, which is the probability of your bit being 1 or 0, whether it is 50%. So if you toss a coin, right, we can only call it really a random test if you have equal likelihood of getting a head or tail, right? If the coin is biased, like what was used in Cholet, which has head on both sides, then no matter whatever how many numbers you toss it, it will always throw you a head, right? Then the probability of getting a head becomes 1 and probability of getting a tail becomes 0. Ideally, the probability of getting a head and tail should be 0.5 and 0.5. So if you have P equals to 0.5, P is the probability, then you have maximum entropy, right? So this is what we have to test. So we found that these GFET arrays right? Each GFET array we calculate the number of ones and zeros, and we found that they are nearly 0.5 the probability, so their entropy is close to 1. Okay, that means that GFET array. This is something you have to test. You cannot just claim anything to be a PUF. So these are the tests you have to do and show your reviewers that okay, you have done all these tests and now you can claim that this is a physically unknowable function. So entropy, the first important thing, right? So they have to have a near ideal entropy, and this is something your software generated ones will never achieve such a high entropy because they are being generated by algorithms. The algorithms might be very difficult, and that's why you may not be able to easily get it because a lot of computation needs to be done. But a hardware one is it's like natural. You cannot beat it because there is no algorithm which you are using to generate this Graphene array, right? You get whatever you get. Okay? That's the uniqueness about hardware based PUF. The next is something we call the Hamming distance. Okay. Now I will define the Hamming distance. The Hamming distance is what is the number of bit flips you need to do in order to go from one key to another key. Okay. Let's say I have two keys and both keys are exactly identical. 4 zeros. Now I am only giving the example using just a 4-bit key, okay, and that can be expanded to 64-bit key. So now here, what is the Hamming distance? Hamming distance is 0 because you do not need to do any bit flip to go from key 1 to key 2. So therefore, what is the number of trial you need to do in order? If I know key 1 to predict key 2, how many trials do I need to do? Just one, correct? But then if I give you a key where the key has all 4s and all zeros, then what is the Hamming distance? 4 because I have to flip 4 of these bits. But here also what is the number of trials? Just one because I know if I know the Hamming distance, right, if I tell you the Hamming distance is 4, then you know that I need to change it 4 times, right? So knowing the information about one key and this Hamming distance, correct, will allow you to know the number of trials. This part clear? Okay. But now let's say for example if I give you these two keys, okay, and I tell you that the Hamming distance is 2, okay, maybe let's not look into this, okay, I will just do it in the board. I give you a key which is 0101 and then I give you this information that Hamming distance is 2. Can you predict key 2? Second key. Okay, you tell me one, where you have to change 2 of these. 2 means that you have to change 2 of these. Okay, so you predict 1. 1, so I already flipped this. One distance is done, then? Okay, you want to predict something? 1, 0, 0, 1. Anybody else? 1, 0, 1. No, then you are changing all the bits. That is not allowed. You can only change 2, right? So anybody else wants to give a try? 0, 1, 1, 0. Okay. So now you see the problem is that, but what is the key then? If I were to tell you that key is this, key 1 is 0, 0, 0, 0 and Hamming distance is, let's say for example 0. If I give you this two information, you can easily, there is only one solution, right? It should be this. Get it? So does it lead to a conclusion that what should be my Hamming distance for a 4-bit key to require maximum number of trials? These are all trials, right? You are trying, correct? So this comes, so if I give you this problem that I have n number of bits, right, what should be my Hamming distance to require maximum number of trials? Hamming distance of 1, okay, let's see, let's do that exercise. Okay, let's say my key 1 is 0, 0, 0, 0 and the Hamming is 1. Can you predict the key 2? What will be the options for key 2? There are 4 options, correct? There are 4 options, right? 0, 0, 0, 1 or 0, 0, 1, 0, 0, 1. 4 options, correct? So on what basis are you calculating of this? What are the 4 options you are calculating? Using this formula 4C1, correct? So therefore, if the Hamming distance is 2 and the bits is 4, then there are 4C2 choices, right? Correct? 4C3, 4C4, right? So therefore, what will be the ideal number, which will give you the maximum trial among this? 4C1, 4C2, 4C3, 4C4, and of course 4C0 is there, right? This one, correct? This one will be 6 because this is right. So if you have a key of length n, your Hamming distance should be n by 2, half. That gives you the maximum number of trials, because you want to make your adversary's job the most difficult one, correct? Make sense, right? So therefore, if you have a key of length x and the Hamming distance is x, then the number of keys required is number of trials required is ncx, and the maximum number of trials will be required when x is equals to n by 2, right? So in a GFET case, n is 64, so the maximum we should get nearly 32, right? And 64C32, look at the number of trials that is required to decode becomes 10 to the power 18, right? And if it goes to 124 bit, it will be even larger, right? So if you now, once you have these keys, you have to test this. What is your Hamming distance, right? You just write a computer code and find out, what is the number of keys, because you already know your keys, right? Because that is what your hardware generates. You just check whether the average distance between key 1 and key 2 is 32. Make sense? So that is the second rule. The third one is correlation. How related these keys are, correct? If both keys are exactly identical, they are absolutely correlated. The correlation coefficient is 1. If they are exactly opposite, the correlation coefficient is -1. Right? This is just a mathematical formula of correlation, and the correlation is 0 only when, again, half of them are different. Okay, then there is no correlation. So this is not like the Hamming distance. You have to really look into there is this function called correlation. Okay, you have learned about autocorrelation. Lots of different types of correlation is there. Here we are looking into the cross correlation between the different keys, and the correlation has to be 0. You should not be correlated. Okay, you can also show that the GFET arrays are uncorrelated. So once you have established these 3 things, then you have convinced that this can now be used as a hardware physically unclonable function. And now you can remove GFET and put any nanometer in your channel, and just create an array of these, measure those IV characteristics, digitize them, and then create these keys and check all this. That's it, right? Then you can do a physically unclonable function. Now these GFET arrays are also very interesting because they are reconfigurable, which means that if your key is compromised, let's say for example somebody know that the key for this chip is this one. What do you do when your password is compromised? You go and change it. But now the problem is, if it's in the hardware, right, how will I change it? It's already there. If somebody knows what are the currents from each of these devices, then they have really accessed my chip, and I have no way to kind of recover it, right? It is compromised means it's fully compromised. These GFET arrays are very unique because you can actually reconfigure them. If you apply a large voltage pulse to graphene FETs, because of this memristive property of graphene, which we did not talk about, but some of you are interested in memristors, I know. So memristors can also be used for physically unclonable functions. So once you change it, right, because it goes into a different state, right, and each device will go to a slightly different state. Okay, so therefore you can create a new key, and you can show that the new key that you create is also kind of follows all the principles that we talked about. The entropy is large, the Hamming distance is kind of 32, as well as they are not correlated with the previous keys, right? Which means that you can have hardware keys which are also reconfigurable. Which means if it's compromised, you just simply go and reprogram your graphene device. Then the the key is again recovered. Just by applying bias. Like in a memory strip device, you apply, this forming process and, different cycling processes are going. I do not know how much you have seen memory strip devices, but even if you measure the memory strip devices for multiple cycles, there will be a band. So after every cycle, the conductance is a little bit different. You see, it's not exactly the same, and we are using that variation. So if you do not make a good memory strip, then you are even better, right? Because every time it will give you a different result, right? But once it is there, and if you do not form it every time, it will keep giving you the same result. It's almost like a non-volatile memory, right? Which is programmable. Right? The number of states it can go through, you can have that many number of reconfigurability. Okay, yes. Then also you will change, yeah, you can change both the voltage magnitude or the pulse duration to program the memory stress into different states. Right? So but the take home message is you can actually get reconfigurability in a puff, which is not possible with silicon puffs, because silicon is not a memory strip material. You see, so that's the advantage of 2D material, because otherwise you will say, why are you doing it with 2D material, right? The idea is that 2D materials gives me this opportunity of reprogramming the device. Correct? So if you are more interested, we have written 2 papers on this. Okay, one, this Nature Communication paper is about graphene memory stress, and this Nature Electronics paper is about the puff, graphene based puff, reconfigurable puff. Okay, it was almost like 4 years now. Okay, and then I think you can keep reconfiguring it, and that's what we show. Okay, this is not as important, but you can not only reconfigure once, but you can reconfigure it multiple times. Okay. Because more number of times you can reconfigure, the better it is. That is something we can do with this puff. And then there are other things that you have to check, because you asked about reliability. Okay, so this has to be reliable with different voltages that I apply. The conductance should not change. And graphene is good because it shows a linear IV characteristic. So when you are working with memory strip based puff, make sure that the memory strip has a linear IV characteristic, right? So because then, even if the voltage changes a little bit, your conductance is not changing, right? Your current can change, but your conductance is not changing, right? That is one. You have to also show that the devices do not change too much with temperature, right? Because you do not know at what temperature the chip will be accessed, right? So your puff should remain same with temperature. So we show that it is stable with temperature, and these are essentially the reliability. Almost 90 to 100% of the cases the puff remains the same. Some changes will happen because this is hardware. You have to deal with that. So GFET puffs are reliable against supply voltage and temperature variation, which is also very critical for a good puff. Okay, and then finally comes this part. Okay, is whether they are resilient to machine learning, because nowadays we may not need to do all this Hamming distance calculation and stuff. Can we train, let's say for example, I collect a lot of graphene device data, this variation, train an artificial neural network, right, and ask it to predict, what will be the next key, or what will be the possible keys. And this is something that we have to check. So here we are using something called a regression based machine learning. I will probably not go into the detail of that. So what we are doing is, we are essentially, these are all the estimator functions and stuff. So we are saying that we are going to predict up to a certain part of the key, okay, and then can it learn what will be the following keys or the following bits. Okay, that is how we train it. Actually, you see, these are the estimator bits and these are the predicted bits, right? So for example, not everybody needs to know your full password, but if they have a part of your password, the life may become actually easier, right? So that's what we are trying to do over here, and we actually show that there's a lot of results over here. Don't get overwhelmed by this. If you're interested, you can read the paper, that this is actually resilient to machine learning attacks, because this is coming from natural randomness, right? There is nothing to learn about. You see, because it is natural, right? I mean, machine learning cannot learn it. Machine learning could only learn it something when there is some underlying physics or something is going on. This variation is kind of random, right? So therefore, we show that, okay, at least the regression based machine learning or the support vector machines cannot actually learn these things. And then we go into even powerful machine learning tool, which is this generative adversarial neural network, or GAN. Okay, this is those where when you ask ChatGPT to produce a picture of something, right? It uses GAN, generative one, right? Because at the end of the day, all our innovation comes from the generative part of our brain, right? Because it is not something we have seen earlier, but we can create, like a poet or a novelist or a music director, right? They are creating something, right? Literally out of what? Out of literally nothing, right? Or maybe their knowledge or whatever it is. So here, these generative networks are actually becoming extremely powerful. All this, deep fake is this technology, right? It can create things which will look like it was created by, Picasso, for example, right? The art piece being created by Picasso, right? So we thought about, can this GAN create keys knowing something about the graphene devices, right? Because then we have again lost it, right? That also we kind of showed that it is not possible even to use the generative AI to create keys which will match the keys that I am generating from my device, right? So that kind of also shows that this puff is actually extremely resilient to even the most sophisticated machine learning attacks. Okay, machine learning attacks are actually very common nowadays. Okay, and with all this ChatGPT, it's going to become simply even more easier. So that's what we kind of showed in this particular paper. And as I told you, you don't have to restrict yourselves to graphene. We can also use MOS2 devices. You see, MOS2 devices also show device-to-device variation, correct? And then we can create similar puff, but now it's the MOS2 array. If you are working with any other material, you can use that too, right? And create the same matrix. It doesn't have to be just 2D material. It could also be other than 2D material, but you have to prove that this other factors that I spoke about, the entropy, Hamming distance, correlation, machine learning attacks, they can survive. Okay, this part is all good. This is what we show over here. Like the Hamming distance is like half. So this is all about physically unclonable function. If you have any question, ask me. I will go into the next topic on hardware security. Any questions about physically unclonable function? I feel like this is something a lot of you who are working with materials can actually do. And it doesn't always have to start with IV characteristics. You can also use Raman, PL, XRD data in order to create that puff. Because if you measure the same device, that's the same material that you're synthesizing, and take the Raman at different locations, the Raman peak position will be slightly different, right? And there have been papers where people have actually used that to create physically unclonable function. Because then it is like an optical puff, because your input is kind of a light and the output is also you are measuring some of the vibrations, right? So you can really use any kind of a technique even beyond IV to show that it is a random entropy source and it can be used for physically unclonable function. Okay. Yes. No, this is to authenticate. Because let's say, for example, if you have chips from Intel, right? And then there's a startup company which is also making a chip, but they could package it in the same location, and they could bribe the packaging facility so that okay, you put the Intel cap on our chip, right? So now if somebody comes to you and sells you that chip, you will not know which is actually an authentic Intel chip. But then Intel can tell you that okay, in my chip, you should be able to use this password to make it work, because we have put these graphene devices, and they don't have to even really tell you what is there, right? They will just make this kind of an arrays of devices, and they will measure and know the key, and then they will tell you this is the key that should be there in our chip, which is not available to your advisor. Even if they make a graphene chip and put their graphene devices, it will not be the exact key. You see that, right? So that is, yeah, this has nothing to do with the functionality of the chip. This has to do with the authenticity, and this is a big problem in the industry right now. Could be good, yes. Optical would be easier. Optical would be easier, it is just that it has to walk through your packaging, because the packaging material is often not transparent. Correct. Agreed. You can, I mean, there is a pros and cons in both aspects. I think as long as, I mean, whenever you put the chip on a printed circuit board, you have access to the IV characteristics of the chip. It is much simpler to do it using IV than using, optical methods. Because at the end of the day, it will be integrated into some circuit, right? And you need to simply write a code to first check whether it's an authenticated chip or not. Possible, yeah. Okay, this part is good, right? Okay, so now next we will go into the next topic, which I call camouflaging, which is to prevent reverse engineering. So what is reverse engineering? Reverse engineering is, let's say for example, you have a circuit, right, which is designed by some US engineer, and then it has been sent for production. Somebody actually kind of open up all the packaging and sees what is the configuration, and then they start claiming that this is my design. Okay, and then they can sell it at a lower price to someone else, right? This is reverse engineering pretty much, right? I mean, so we have to prevent this reverse engineering. And now if I think about reverse engineering, we have a technique called camouflaging, okay, and I will explain that to stop that. Now camouflaging is a concept that comes really from nature, because if you look into this picture, do you see a spider over there? Yeah. Yes, there is a spider, it's a real picture. The spider is camouflaged, right? Why? Because it is either hiding from its predator or trying to catch a prey. And this happens all the time if you go to forest, right? I mean, you will see that a lot of animals camouflage, right? So that they kind of blend with the background and they cannot be identified by their predators, or they can easily go and catch the prey, right? Right? So this is something, so that why are they doing it? They are trying to fool the predators. So in order to stop the reverse engineering, we have to fool our adversaries, right? So this is something I am going to show you now. How can we use unique properties of 2D material to camouflage circuits, so that even if somebody sees the circuit, they will not know how it functions. If they cannot know what the function is, then I have able to kind of fool them. Look at these images. Do you think they are different, or they are exactly identical optically? I mean, there are some shift and stuff, don't forget about that, but the shape, color, they are identical, right? Right. So therefore I have been able to fool all of you right here, right now. Okay, if I tell you that this flake over here is actually an N-type material and this is a P-type material, how is it possible? Looks exactly identical. What I do not know, but now this same thing is N or P. That is possible with the 2D material because of this. If you have not monolayer flake but a multi-layer flake, then this material is primarily N-type. Most of the 2D materials are N-type. Then we spoke about this oxygen plasma treatment, didn't we, right? And when you do treat it with oxygen plasma, it's like a self-limiting process, but you can actually convert the top layer into transition metal oxide, like moly oxide, tungsten oxide. And these oxides are transparent, because most of the oxides are transparent. So therefore the appearance of the flake does not change. So what am I doing? You see 15 seconds, 30 seconds. Remember this timestamp? We are literally doing oxygen plasma. So on top of it now there is an oxide layer which is transparent. So the optical appearance of the flake does not change. But now this material which is on the top converts the bottom material into P-type. It just dopes it. This surface charge transfer doping that we spoke about. So although we started with an N-type material, it has become a P-type material because of this unique property of 2D material, where the oxide is number one transparent and number two serves as a P-type dopant for the underlying material. So I have now camouflaged the function of the material without changing its appearance. Now let's say for example if I go ahead and make a device, right? I do not know whether it's an N-type material whether it's a p-type material, and if I do half and half, how does it become? It becomes a p-n junction, which is a diode, right? So now your resistor, transistor, diode exactly looks alike. Makes sense? So now if I go and start building a circuit, right, I will not know, for example, let me see, there is an example coming up. Okay, these are some of these, more data actually, just showing that what happens. You see pre-plasma, post-plasma, I can use it as a resistance, because generally you cannot change the resistance value of a resistor, right? But now through oxygen plasma, you see, I can get to 2 resistance values without changing its appearance. So your adversary will not know whether it's a high value resistor or a low value resistor, correct? That's one. I could do it for a diode, right? Depending upon how much I kind of dope this side versus the other, right? You can see the 2 diode characteristics are different. So not only that I can make the same device as a resistor, as a diode, as a transistor, I could also make diode with different turn-on voltages, resistors with different resistance values. So I get enormous flexibility in terms of designing circuits, camouflaging their functionality. Okay, I will come to the camouflaging, and these are the transistor characteristics which you have seen. So now you see that if, so here is the number of trials, because for example, if I make a circuit, right, let me draw it over here. So let's say there is a circuit over here, just draw it on this. Okay, let's say there is a circuit element, there is another circuit element, okay, there is another circuit element over here, and I wanted to know if I have a V in over here and I want to have a V out, right? That's what the circuits do. I have an input, I have an output, and there are some circuit elements. Got it? So if there are simply resistors, all these elements are resistors, will you be able to say, what is this circuit? This is just a voltage divider, right? Correct? But if this is a resistor and this is a diode, what will be the output? A lot of you probably have not taken. This is a rectifier, right? This is a rectifier. If this is a NMOS transistor and this is a PMOS transistor, then this is a kind of an inverter, right? So depending upon what these elements are, the function of the circuit, the output input are changing, right? So for you to know what is the output for a given input, you need to first know what these elements are, correct? Understood, right? So if each element looked different, then by looking at it, you will be able to tell, oh, this is a resistor, this is a diode, so this is the function. But if you do not know any of this, how many trials will you need in order to find out the actual input output? Because then you are predicting. Let's say this could be, for example, there are 3 choices: resistor, transistor, or diode. So can you tell me for this circuit how many trials will be needed to find the right input versus output? Anybody? It's a math question though, no device question. There are 3 possible choices for each of these elements. How many trials will be needed? Huh? No? Huh? Factorial for no? Factorial for no? Huh? Exactly. Very good. 3 to the power 4, because for each choice here, I have 3 choices here, 3 choices here, 3 choices here, right? So 3 to the power 4, right? This is what I am showing, that if there is a circuit which has p elements, right, p of those, and each has got m functions, right, then this is the number of trials. So you see the idea of camouflaging, right? So if everything looks alike, it is just that it becomes exponentially difficult for your adversary to figure out the function. And this is something that I have shown you using a simple circuit diagram. Here there is only 2 elements, right? So here is a resistor and here is this camouflaged element. If this camouflage element is a resistor, then it's a voltage divider, and if it's a PN junction diode, then it's a rectifier. The output is very different. So what did I accomplish? I camouflage my circuit. Isn't that true? So I don't care about reverse engineering, because you can look, what the design is, but you will have to go through this many trials to tell me what it is actually doing. Correct? And the same thing applies for even bigger circuits. You see, this is something a lot of you who are from electronics background have seen. This is an R2R ladder, correct? Right? And this is generally used for digital to analog conversion, right? These are the digital inputs and this is the analog input, correct? But then if I change that R2, you see if R1 by R2 is 2, this is your R2R ladder, then it's a digital to analog converter. But as I told you, I can even change the resistance value without changing its appearance. If I make this R1 by R2 much greater than 2, then look at its profile. It's actually a counter. You see? So whenever you have 1 1 in the sequence, it will be 1. If you have 2 1s, then it increases. You see? All the 2 1s goes here. If you have 3 1s, then they are here, and all the 4 1s. The counter. How many 1s are there in your bit sequence? So completely changed functionality, right? Without changing the circuit architecture, which are vulnerable to reverse engineering. You see, and what are we using? Very unique property of this 2D material. Make sense? This camouflaging aspect is clear, right? So this is another aspect, and now you can start doing it. You know, this is an overview of a camouflage circuit. So here, forget about this. If I create a circuit like this, because all our AND gate, OR gate, XOR gate have a particular structure, right? How they are arranged, correct? But now, if these are all kind of question marks, I can use a generic structure, and then I can create individual gates just by, yeah. So therefore, the OR gate, XOR gate, NOR gate, XNOR gate, everything is going to look alike, right? So I can completely fool my reverse engineer. That's the thing that we are trying to do. The only way to find out, you know, whether there is something going on, you can now start taking some SEM images. You can start doing some AFM because the height will be a little bit different after the oxidation, right? Or you can even do, you know, let's say for Raman or PL, correct? And then you can find it out that, oh, this material has been oxidized, correct? Material characterization. You see pre and post plasma treatment, the Raman shift is there. Then you can say, but think about in your integrated circuit, how many transistors are there? 1 billion. Are you going to take SEM image of 1 billion transistors? Are you going to take Raman PL or, you know, AFM image of 1 billion transistors? You can, if you are given, you know, the edge of the universe, right? So nothing is ever foolproof. But the question is, you know, how much time and resource your adversary has to invest in order to decamouflage it, right? You just have to make it is always the running between the cop and the thieves, right? You have to be ahead. You have to be well ahead. If you are the thief, you have to be well ahead, right? So that the cop can never catch you. So they actually, I mean, will actually take cross-sectional TEM, SEM. They will open up the chip, and then some countries have resources and human power. Okay. Yeah, yeah. You see, it is also not about. It is also not about really. You know, you need to know every details of the chip. If you know some details, then you understand, right? Because, you know, your chip is not going to be unique at every unique position. Makes sense, right? I mean, this what happens to the bullet trains, right? Was discovered by the Japanese, and then bullet train is there in somewhere else at higher speed. Yeah. Okay. So reverse engineering could be useful if you could do it properly, right? Okay, so this is what it is, and the other thing, yeah. Yes. But in this case, I mean, yes, in principle, but in this case, you have to go, and because every device, the resistance is also changing. That they may be able to figure out that, okay, it has been plasma treated, okay, there might be some shift, but how will they figure out, you know, really how much plasma treatment was there? Because you saw based on, if I go back to this plot over here, right, just a simple resistor, right? We are talking about a simple resistor. You see, depending upon the plasma treatment time and the thickness of the initial thickness of the flake, the resistance could be anywhere. So even if you do a Raman, you might be able to say, okay, I know that it has been plasma treated, but how do I know what is the exact resistance value? And as I told you that R2R ladder, if the resistance values are R versus 2R versus, then the function is completely different. So even if you do that, it is even more foolproof. It's difficult. This is where I was talking about, this number of trials that is required, right? Remember this plot that I showed? Yeah, this one. Well, it depends upon what philosophy you want to follow, right? This is a discussion off the camera, not on camera. We can have. Okay, so this is what it is. So I have told you two different things, and then let me skip this part because this will be too much. I will go to the summary. So you see that hardware security is absolutely important, and then I think 2D materials could be a rescue, both from the point of authentication as well as preventing the reverse engineering of these different chips, right? And you can also use other materials. We are working on 2D materials, and if the next generation of technology is 2D, then it is better to do everything in 2D, but it doesn't restrict the use of other kinds of materials for this hardware security application. Okay, with that we'll end this lecture and then we'll continue.